Okay, since I've laid so much complicated stuff on you, we're working through easy stuff now. Give you a chance to get everything in your head, working the idea of proof. So, determinants. Leaving out letters. Especially between two E's. A determinant of A first of all, it's got to be a square matrix. So we have A11 through AN1 in the column and A11 through A1N in the row. So forth. It's just denoted by putting the numbers between two things that look like absolute value signs. But they're big and long so they can accommodate all the rows. Okay, so here's the definition. Determinant of A, B, C, D in this order is AD minus BC. Okay? Okay, typical 3x3 matrix. The determinant of that is -1 to the 1 plus 1 times A11 multiplied by the determinant you get when you eliminate the row and the column of A11. Okay? And that would leave you A22, A23, A32, A33, right? So just this determinant, that if you wipe out this row, you wipe out this column, whatever's left, there it is. So that's this. Okay? Well, that's the first part of it. Then you go to A12. And you do the same thing. We use 1 plus 2 here because it's 1, 2. Okay? Over here, what do you think we're going to put over there? Going to be a 2 by 2 matrix. How are we going to get a 2 by 2 matrix? Corresponds to A12. What do we do for A11?
We eliminate that.
Sorry?
Do we eliminate A11?
We eliminated the row and the column of A11, which totally eliminates A11. Of course, we've got A11 here, but this is what we get when we eliminate the row and column of A11. So here, we've got this. We're going to eliminate the row and column of A12. Leaving us what?
A21?
Good start. So we got A21, then what?
A23?
Yep. and A 3, 1,
A through 3.
A through 3. We wipe out the row and column of A1, 2. Okay? So what do you think the next thing we have to write down would be?
A1, 3.
Well, we're gonna have A1, 3. But we're gonna have -1 raised to the power, what power?
1 plus 3.
Yeah. And then that's times what you get when you take out the row and column of A1, 3. So that's gonna be A2, 1, A2, 2, A3, 1, A3, 2. Okay? That make sense? I mean, you don't necessarily understand why or what it means, but that makes sense. The pattern is not hard to see. Now, you don't have to do that on the first row. You could do it in the second row, or you could do it in the third row. As far as that goes, you can do it in the first column, second column, or the third column. Any row or any column. Okay? That's the rule. Easy to apply. Tedious, but easy. Now, if you had a 4x4 matrix, then when you wipe out the row and the column, it leaves you a 3x3 matrix. And you're going to have 4 of them. So you're going to have 4 3x3 matrices, each of which reduces down to 3 2x2 matrices. So you're going to have 12 2x2 matrices to do. Okay? Now if you have a 5x5 matrix, you're going to have 5 4x4s, each of which ultimately takes 12 2x2s. Okay, so you're going to have 60 2x2 matrices. And by the time you get up to a 10x10 matrix, you've got over 3 million. Okay?
Yeah.
Actually, yeah, well, it grows fast. It's a factorial. Okay? So it gets nasty. So you're not going to use this to do the matrices. Okay? What you're going to do is you can reduce a 10x10 matrix in a reasonable time. It'll take years to reduce it, to do this to a 10x10, and then you'd make mistakes. You know, I wouldn't. You might. Okay. Well, I will. And you don't so much. Okay. The easy way to do it is you just row reduce the 10x10 and keep track every time you multiply a row by a number. Okay?
Okay.
And then you put those numbers together. Okay?
Okay.
You also want to keep track of when you interchange rows, because every time you interchange a row, you add a negative.
Yeah.
You write a negative one. Okay? That's it.
Okay.
If you add a multiple of a row to another, it doesn't change anything. But multiplying a row by a number does, interchanging rows do. You just keep track of those numbers, and you got the determinant. Okay? So, much easier. Okay? Meaning of the determinant of a 2x2, remember 2x2 can be represented as a mapping from R3 to R3. You got that unit circle that maps onto the ellipse. Okay?
Okay.
What's the ratio of your areas? And not just the areas of the unit circle, the area of any region of the plane. So if your determinant is 3, it means everything gets 3 times the area. It also gets distorted, typically, or rotated, okay? And you want to decompose matrices into rotational and non-rotational components using eigenvalues and all that stuff, okay?
Okay.
And that becomes pretty challenging when you get into bigger, higher dimensions. It's not as obvious. And 3 dimensions of determinant, well, the same thing you did with the unit circle. The vectors around the unit circle map onto vectors that define an ellipse. Well, the vectors of the unit sphere in 3 dimensions map onto an ellipsoid. Distorted in this direction, distorted in this direction, distorted in this direction, and typically rotated. Okay? So, that's all there is to it, though. Okay?
Okay.
And that's and the determinant gives you the ratio of the volumes. Make sense? Haven't proven it, but the idea, just the connection, because you can understand how you get an ellipsoid 3 dimensions, and then in higher dimensions, well, you have the innate hypersphere to a hyperellipsoid. Okay?
Okay.